So for this one, if we're finding an approximation, right, we can't actually find the full value, but if we find an approximation for it, how can you approximate a tangent line? How else can you, okay, well hang on, let's go right back. A tangent line, a derivative, what were we thinking about? Two main ideas. Two main ideas. You see that symbol? What are the two ideas that have to come to your mind? Rate of change, and the other one is going to be more helpful to us in this case. The slope, right? So how else can we, if obviously without a calculator, we're not going to be able to answer them in this question, right? Because we can do this derivative. We know that f prime of x is going to be natural log 10 times 10 to the x, but we need a calculator to tell them the natural log of 10. And we need a well, we don't need a calculator for 10 to the 1, but so that's not going to help us. How else can we calculate, and in this case, approximate, which is the actual language they're using? How do we approximate a derivative, or the tangent line, or a slope? Guess. Well, remember, guessing may cost you a quarter point. Yeah, it's going to be kind of like differentials. Remember, we use them to approximate with a line. Well, for this one, what you want to think about is, we know what this graph looks like. It's an exponential graph, okay? And I really wish that I could get this from it, but I can't, not without a calculator. So how can I approximate it? Well, what if I'm really, really close? If I take 2 points that are really close together, then those 2 points will possibly give me an approximation. That's what we have to do here. So it's hard to see, but there's a point given to you up here. It's the point 1.04 and 10.96. The other point, if we plug in at 1, the value is 10. So what I'm going to do is I'm going to use plain old-fashioned slope, which is to go, to sleep. Which is to go 10.96 minus 10 over 1.04 minus 1. So I would end up with 0.96 over 0.04. So that's 96 out of 4. So 80 is 20. 16 more is 96. So that would be 24 out of 1, if I reduce it. So the answer, I hope the answer is 24. Is that?
Yeah, it is 24.
Yes. So for this question, unfortunately for us, there isn't an easy way to answer this. But unfortunately, it's not a part of math that we learn anymore, so we have to go about it a different road. So I'll tell you the easier way after. But what we have to think about is, these are our possible solutions for this differential equation. So what you might want to think about to yourself is, first of all, it has to be that the derivative for these questions lines up to the slopes shown in the picture. So let me just draw for you a possible initial condition, one of the ones that might have been there. Okay, so let's just start with this. Okay, this is not the proper initial condition. I'll show you what the proper one would look like when we get to that shortcut. But okay, this graph here, what kind of graph is this? Part B.
Here.
A line, yeah, it's just a simple line. Everybody see that's just a line? Could this possibly be the solution if it was a line? No. What about this graph here? Do you recognize what kind of graph this is? Like, what if you had to put it in your graphing calculator? What would the equation look like? Right? If we had to put it in the graphing calculator, this is what you'd have.
It's like
Yeah, it's one of those reciprocal graphs that we did in Math 12, right? One that goes kind of like this. Could it be that as the reciprocal graph? No, that's not the reciprocal graph either. It would have to go like this and like this. Okay? So it's not the reciprocal type of graph because it's clearly not the right slopes. Okay, there's another graph there you recognize. Oh, it's good. What did you recognize?
Parabola.
Okay, hold on to that thought. Parabola. So here's the parabola, which is the one I expect people would recognize. Okay, could it be that there's a parabola here for the solution?
Yeah.
That one looks kind of like a parabola, right?
Yeah.
But unfortunately, in our case, this isn't going to produce the same picture. Because the parabola you're thinking about here, this parabola can only look one of two ways. It can look like this, or it can look like this. It cannot do the sideways one, right? That is not the same picture that I'm showing you here. If it's in this form, it's vertical. Okay, the horizontal parabola, if you want it to go horizontal, this is the equation it would have to be, right? It would have to be squaring it this way. So it couldn't be the parabola either, otherwise this wouldn't be possible in my picture. The fact that it's possible tells me it couldn't be the parabola. Okay, so now we're down to two possibilities. Okay, at this point, you should recognize one of them, I hope. Is there one, just hold on to that thought. Do you recognize between these two that are remaining what kind of pictures they might make? Good. It's actually going to be, wow. It's actually going to be a circle, but it's going to look like an ellipse. The reason it's going to be an ellipse or an oval is we've messed with the x-coordinate. So all that's going to do, if you think about your transformations, it's going to squish the x-coordinate, right? I'm squishing it right now. Vertical factor will be 1/2, horizontal would be messed around there. But anyways, the point is, it's going to be a circle or an oval. Could you draw a circle or an oval in this picture? No, that means the only possibility by process of elimination is D that we could have. Okay? Now let me show you another strategy for this question which would also help you answer it. Now one thing you may want to notice here is that as I'm on, my slope fields on this axis are vertical, and my slope fields here are horizontal. Okay? So let's just ask ourselves, right, what we do is we put in the values of x and y, and they produce these little slope fields, okay? So how could I make a relationship, so that no matter what value of y I give you, it's always a 0 if I'm on that value for x? Like, what could I do? Like, if I put in the value here, this would, I don't know, it looks like maybe it's 0 and -4, and you still get 0. 0 and -3, and you get 0. Okay? What do you think? Okay, maybe we need to look at this axis as well. How do you get a vertical slope? Yeah, see these slopes here? They're all vertical. How do you do that? What makes it go vertical? Pardon me? Well, in this case, y is 0. Dividing by 0 makes it vertical, right? So this is hinting to me that I divide by y, because when y equals 0, I get a vertical slope. If I'm here, this line here, which shows me the horizontals.
So is it like x over y?
Well, that's where I'm getting to, is this is going to be approximately, there might be some constant in front, right? It might be 2xy, it might be 5xy. But this is approximately what I'm modeling by the slope field. So it would be equal to some constant. So for our purposes, we could make it a 1. Then that means if I wanted to do a differential equation, sorry, let me just see here. You know what, I gotta pause the video, I think we're out of time.